one of the fundamental building blocks for this numerical lifting line method is a vortex segment. So we're going to talk about a vortex segment in just a moment here, or work through some of the things we can learn from a vortex segment. We're going to find that our new numerical lifting line algorithm is made up of a series of vortex segments. Okay, so let's just take one segment here for a moment and look at the influence of that segment on some point in space. And this segment is going to have a direction. This vortex has a direction, and according to the right-hand rule, it also we can show that the vorticity gamma is rotating around according to the right-hand rule. I've just drawn gamma in the positive direction there. So what we want to do is figure out what the induced velocity is from this vortex segment on this point here. So let's just make a couple different definitions here. We're going to say that L is this vector that defines this segment, and we're going to divide this segment up into little pieces, and we're going to call those DL. So those are our small vector segments. For each of those vector segments, we're going to draw a straight line to that point and call that R. And that is also a vector. And we're going to define a couple other vectors on here. This is R1. That's where the vector, or the vector from the beginning of the segment to that point. And then R2, we will draw as this vector here from the end of that segment to that point. Okay, so from the Biot-Savart law, we can say that the differential velocity that is induced at this point by this segment here, we're just going to take this a segment at a time, or this differential segment, I should say. The differential velocity produced at that point by that differential segment is equal to gamma over 4 pi, and then in the numerator we've got dl, the differential segment, cross r, and in the denominator we're going to have the magnitude of r cubed. Okay, so this is the differential velocity induced at this point by this segment here. So what we want to do then is simply integrate to get the whole velocity. It's simply the integral of that differential velocity as we integrate now across the length of this of the segment. Okay, so in order to do this, we make a few different we write out a few different definitions here. So for example, we can say that dl is equal to L times d zeta. So we can use zeta as this variable of integration as we move along the segment there. And then we can say that r at any point is equal to r1 minus zeta times L. And then we can say that L is equal to r1 minus r2 . And finally, we can apply a bunch of trig identities. So I'm not going to work through all of this math, but these are the things that are useful in working through this math to actually solve this integral. And when we do that and apply these identities here, or these definitions here, what we get is that the velocity induced at that point by that vortex segment, by the whole segment, is equal to gamma over 4 pi times r1 plus r2. Those are the magnitudes, r1 plus r2, multiplied by r1 vector cross r2 vector, divided by r1, r2 magnitudes, plus r1 dot r2 vectors. Okay, so this is a really useful equation that we're going to apply in this numerical lifting line algorithm. And then another really useful form of this equation is actually what we get in the limit as in the limit as R2 approaches infinity. Okay, so we're going to call this a semi-infinite vortex segment, and this is the limit as R2 approaches infinity. So if I were to redraw this segment over here, we have our point of interest, and here's R1, and then we'd say that this segment goes off to off in some direction for an infinite distance, so that R2 here is an infinite length. Okay, so we can take the limit now of this equation here that we've developed, and in the limit as R2 approaches infinity, and we're going to say that the direction here in infinity is u infinity. Okay, that's the direction of the free stream velocity in the numerical lifting line algorithm. So we're just going to plug that in right now. That's the direction that will have these trailing vortices headed in is u infinity. So we're just going to say that it goes off to infinity in the direction of u infinity, and what we get then for that is that v at that point, the velocity induced at this point of interest, again, is equal to gamma over 4 pi times u infinity cross r1 divided by r1 times r1 minus u infinity dotted with r1. Okay, so this is also a very important equation that we'll be applying in the development of this numerical lifting line algorithm.